Hello, students. We are going to start talking about space today, and we're going to go and work our way through it. So we'll have a couple of videos because it's going to cut out. We'll have some videos within the video, and hopefully the audio and video quality is good, but we'll give it a try today. So we're going to be talking about, for the next several weeks, the scale of our universe and how big it truly is and how small we truly are. So when we start talking about the scale of the universe, we know a little bit about it, but there's a lot of things that we have to infer. So how big is the universe is a question that we frequently get asked. So when we look at the scale of the universe, it's hard to tell exactly how big that would be. And we truly don't know. Our best guess right now is 4.46 billion light years. So in other words, if light left Earth right now and traveled at the speed of light, it would take 46 billion years for it to get to where the edge of the universe is at, or the observable universe where we can actually see. But obviously no one's that old to actually know if that's accurate or not. So we do know a few things. For example, just to kind of give you a perspective of how long it takes to travel in space. We had a New Horizons spacecraft that was launched January 2006, and it finally arrived at Pluto in spring of 2016 to collect data. It was a 10-year flight, and you're like, well, that's got to be at least a light year. No, not even close. You can see right here, this is how long it took for it to get, that's how many light years it is. Nowhere close to 1 year. We could actually measure it more accurately in light minutes. So it takes 327 light minutes for sunlight to get to where Pluto's at. And it takes about 8 minutes for light to get to the Earth. So that kind of gives you a little bit of perspective. Very, very close, and it takes 10 years to fly that far. So we're talking about an enormous space if we're talking 46 billion light years to get to the end of our universe. However, we still are very curious about this, and we are making all sorts of theories to try to explain this. Maybe some of these you've heard of: the Big Bang theory, string theory, the horizon theory, quantum theory, relative theory. We're going to talk about a few of these as we go through this chapter, not all of them, but we are going to get into some of them, and all of these theories have problems with them. They don't work out as they would hope. So none of them is a perfect theory. They're still searching, trying to figure out what took place, how it got to how it is today. All of these are attempts to make, or try to make, us be able to understand what took place, even though we weren't able to see it. It was long ago, and we're trying to rationalize what took place. So remember, these are limited observations, and we can only get limited information from them. Like having only a couple puzzle pieces. It's hard to solve a puzzle if you only have a few of them, trying to figure out what's on the whole puzzle. Here's an example. So I wear size 15 shoes, like many professional basketball players. I am taller than some professional basketball players. I can touch the net while standing on the ground, yes, on my tiptoes. Therefore, due to all of these qualities, I must be able to play and dunk a basketball like a professional basketball player. Yes, of course, right? Well, no. Truth be told, I can't even grab the rim. I've got no spring in my legs, and I can get near dunking a basketball unless I'm on my trampoline. That's about the only way I can dunk a basketball. So just because I can observe certain qualities doesn't mean that we can infer correctly the outcomes. Here's another thing. All the time we're getting these kind of reports in the news. Astronomers are discovering Earth-sized planets, and they are in regions that have moisture in them or ice. So there could be water there, and there's a certain distance from their star. So therefore, could there be life there? And more than likely, you've heard certain questions like this. And astronomers are very curious about it, trying to figure these things out. But there's more to it than just the distance from a star, more to it than the size of the planet, more to it than the temperatures that are there in order to support life. And so we have to keep that in mind as we start looking at all these different theories. Now, we're going to watch a video here, And this video is going to help us try to get a perspective on how big the universe truly is. Because that 46 billion light years, I'm sure to all of us, means nothing. And so this scientist is going to try putting it in perspective a little bit here of how big that truly is. So here we go. Maybe.
You'll never, ever get your head around how big the universe is. Don't go there. It's just vast. It's enormous. There's no way a human mind, I think, can actually comprehend the true immensity of the universe. We're happy with the size of an elephant, or the size of a tree, or maybe even the size of Durham Cathedral. But I think if we go beyond that, then our brains just start to run out of gas.
It may be difficult for our brains to comprehend, but that hasn't stopped astronomers endeavouring to measure the distance to the stars. One technique is to use a phenomenon called parallax.
Everybody can actually experience parallax for themselves. If you hold your thumb up and close one eye, you can see that your thumb appears to be in a certain position relative to something behind your thumb. But then if you open that eye and close the other eye, you'll see your thumb appears to move relative to the object behind.
So give that a try. Hold your thumb up, close one eye, and close the other eye and open the other one up. Does it seem to move? That's what we're talking about here.
The same thing happens when we look at the stars. When we look at a relatively nearby star from the Earth, it appears in a certain position relative to the other background stars. 6 months later, when the Earth is on the opposite side of the Sun, the same star will appear in a different position relative to the background. Like opening and closing one eye, then the other, the star appears to move, and by measuring this apparent movement, we can calculate the true position of the star. An alternative method of measurement is to use certain stars in the sky known as standard candles. We know exactly how brightly they shine. If we can therefore measure how bright they appear to us on Earth, we can calculate how far away they are. The dimmer they appear, the further they are from the Earth.
So the nearest star to the Sun is Proxima Centauri, and that, it turns out, is 40 trillion kilometres away. That's 40 million kilometres away from the Earth.
Such numbers start to become incomprehensible, and that's why astronomers have adopted an alternative unit of measurement for such vast distances, the light year.
If you like, is a time machine.
So I'm going to pause it there for just a moment, just so you have an idea. When they're talking about these standard candles, we've never gone that far, obviously. And so these are all inferences based upon observations that we've made. So
light moving around the Earth in 1 second. So in that time, light will travel around the Earth over 7 times. So that's fast. Speed of light is 300,000 kilometres a second.
So 1 light year is about 9 million kilometres. The speed of light also leads to a curious consequence when we stare at the stars.
So the light from the Sun takes 8 minutes to get to the Earth. That essentially means we're looking into the past. We're looking back at the Sun as it was 8 minutes ago. So if the Sun was to disappear right now, we wouldn't know for 8 minutes. So a telescope, if you like, is a time machine. We're looking back in time, and the further the object is away from us, the further back in time we're seeing it.
Our Sun, like nearly all the stars we can see with the naked eye, sits inside the galaxy we call the Milky Way. But our galaxy is not alone in the universe.
Not